Okay, great. So good morning. First, I would like to thank the organizers of the symposium to giving me the opportunity to give this talk today. My name is David Herreros. I am a PhD student in the biocomputing unit in the National Center of Biotechnology in Spain. And during this presentation, I will be talking about this new method we have developed, the Zernikes3D, which allows us to analyze conformational landscapes from our CryoEM data. So as we all know, molecules are not static. They are continuously moving and changing conformation. And those conformational changes actually change the way the molecules function, the biological function of the molecules. And that's why in CryoEM, we are very interested in trying to address or extract several conformations from our data, which is classically done through 3D classification, which is a good first approach, but is not perfect because we are getting a very reduced number of states. And we know that in reality, molecules move in a more continuous way, like in this video. And this is the objective of this work, is to develop a new method that will allow us to get a conformation for each particle in our dataset, in such a way that we can get a much richer conformational landscape. Our approach is very similar to the Fourier Transform. So in the Fourier Transform, we have, for example, this complex signal. At the end, we are able to decompose it into different sinusoidals that make the analysis much simpler. In the case of the Zernikes3D approach, we have something similar. We have a complex motion, and we are going to use this basis to decompose it into different movements that are much simpler. And from these components of the movements, we can start doing our analysis of how the molecule is actually moving to reach different conformations. And this is a Zernikes3D basis. It is composed by two different sets of functions, spherical harmonics and Zernike polynomials. And the combination of these two sets of functions will give us the different components that are represented, one example here in the image, that will allow us to analyze these simpler motions. And then we can combine all these different components to represent the whole motion of the molecule going to a different state. The objective with this basis is to find a per point displacement. And here, the word point depends on the data you are working on. If you are working with volumes, then you want to find a per voxel displacement. If you are working with atomic structures, you want to find a per atom displacement. But the idea is the same. At the end, you want to find this per point displacement in such a way that you minimize the distance between two different conformations. So for example, if we have the open conformation of one of our macromolecules, and then we have the closed conformation, we want to align the open conformation so it resembles as much as possible the closed one. And this is what we are going to try to find, this displacement of the open conformation towards the closed one. And this is the way we do it. At the end, we are going to define a deformation field, which is this G of L, that depends on our basis and also some coefficients that determine the importance of each of these different components of the basis in the whole motion of the molecule. And thanks to this, we are estimating a deformation field. So imagine we have this very silly example where we have this Eiffel Tower that is kind of curved, and we want to move it towards this Eiffel Tower where it's kind of straight. So at the end, the program will find this deformation field that tells where to move each voxel in order to get this new image. We're going to do exactly the same, but with our conformations. These bases can be applied to volumes, can be applied to atomic structures, but it's all, but here we are going to talk mostly on the topic of particles, CryoEM particles. And here the application of the basis is not so easy because the basis is defined in a 3D space. But if we want to find a per particle conformation, then we have to go to a 2D space. So this application is not straightforward. And this is the process we have to follow. So our program has two main inputs. One is the reference map. Here we have all the 3D information that we are going to use to get new conformations. So actually we are going to move this reference map to get a different conformation of our molecule. And then we need a target particle that should have also alignment information, CTF information, and so on, that represents the experimental conformation we would like to approximate in 3D. So what we are going to do is to take the reference map, and we are going to apply a deformation field that we have computed with the Zernikes3D basis. And this will give us a deformed version of the map representing a whole different conformation. Now we can take the alignment information of the experimental particle and use this to project the map. And now we get a deformed projection of our input reference map. And we can compare this conformation with our experimental image. If the comparison is fine, then great, we have approximated our per particle conformation. We have this 3D conformation of the particle. If not, we can use that comparison to refine the deformation field until we get something that looks fine. However, things are never so simple, and the problem is that we are trying to approximate a 3D conformation from 2D information. And this means that we have to deal with the problem of losing a lot of information due to the collapse of the volume into a single plane, this projection. So at the end, if we have a look at the image, in the plane of the image, we have all the information of the conformation, but we don't have experimental information along the direction of projection. And that means that the program will do some guess in that direction, which is not a real conformation because we don't have experimental information. One way to solve this will be to apply some regularizations, trying to avoid this effect as much as possible, but this is not completely clean. But thanks to the properties of the Zernikes3D bases, we can solve this problem in a very elegant way. This is the way we can solve it. So in the same way, we can, for example, rotate a volume. So it's in a different position. We can also apply the same rotation to our coefficient space. So for example, if we have this map and this set of coefficients that produce this deformation along the projection direction that we would like to remove, we can try to rotate the map and also the coefficients. So now the projection direction matches, for example, the z-axis. And now we know that the deformation field corresponding to the z-axis only contributes to this bad effect of not having experimental information along that direction. So we can completely remove that, then unrotate the coefficient space, and we get a much better and realistic conformation from it. And now I'm going to show you some results we have got with this new approach. The first one is on synthetic data, which is very useful to test that everything is working fine. So here we were working with CCT transition from open to close conformation that was simulated using A&M. And thanks to this A&A method, we were able to get 5 different conformations along this open-close transition. And we use each of these conformations to create projections from them. And at the end, we ended up with 225 projections from these 5 different conformations. And we tried to estimate those conformations using the Zernikes3D approach. And I don't know if you will be able to see it. I have later on a bigger image of this. But we get this representation of the coefficient space in low dimensions. And we are able to identify very well all the different conformations. So this green one, blue one, purple one, yellow one, and the red one. So the program is able to identify very well all these different conformations of the transition. But we can go one step further. And as I have said previously, the basis can work with particles, but also can work with volumes or with atomic structures, which basically means that you can translate any data type into this coefficient space. So this opens the possibility to do combined analysis. So you can see in the same space any heterogeneity information coming from particles, coming from volumes, or coming from atomic structures. And this is what we did here. So here you can see the previous point cloud that was coming from all these particles of these 5 different conformations of the CCT. And now we have some white points that these points correspond to the actual 3D conformations in the Zernikes3D space. So as we can see, it makes a lot of sense. All these particles are surrounding the actual 3D conformation where they are coming from. And this is very useful because it gives us a lot of information on how to analyze the space and see, for example, one conformation that you got from the 3D classification, or even some atomic structures you might be interested in, is actually represented in your CryoEM data, particle data. And now moving to real CryoEM data, we started working with the Empire 10028, which has become very popular to study all this continuum heterogeneity. The idea is that in this data set, there is a ribosome that is defining a lot of different motions, but mostly one is a rotation of the small subunit of the ribosome. And the idea was to take this data set, reprocess it completely, and then get a set of particles that we can fit into the Zernikes3D algorithm and see all these conformational changes. And here you can see the representation of all the particles in the data set. So each point here is a particle in this data set representing a different conformation. And we can see like a big point cloud that represents a model associated to the reference state we have used. And then some other region that is coming out that corresponds to this rotation of the small subunit. And this can be seen here in this video. So it's not only that we can identify this main rotation, but as you can see, we can also get any other possible conformation that is present in this data set. And we did something similar with the COVID-19 spike in the Oneup conformation. So in this data set, we only had particles from the Oneup, and the idea was to see how the RBD moves, the up RBD moves, and explore the different conformations. So this dataset was already analyzed using 3D classification, and it was possible to find two different conformations corresponding to somehow an RBD that was kind of open, and another RBD that were more close and was kind of moving in a lateral way from right to left. So if we use those same particles in the Zernikes3D approach, we get this point cloud. And in this point cloud, thanks to all this process of pulling at the same time the classes and the particles, we were able to identify very well the two states that were found with 3D classification, which are these two here. But also we were able to see kind of a new region that was coming out, represented by very few particles, that kind of completes this left to right motion of the RBD. This is a very subtle motion, which can be seen in this video. The RBD is moving little from left to right. So it means that we can also identify very well these small conformational changes. Up to here, we have seen how to approximate conformations of each particle in our dataset with the Zernikes3D approach. This is already very useful if you want to analyze the heterogeneity of your data. But we can try to go one step further. Now we know how to move the reference map so it matches the conformation of every single particle in your dataset. And the question is, can we go the other way around? Instead of moving the reference map so it matches the conformation of the particle, can we take the particle and correct its conformation so it's closer to the reference map? And this actually makes a lot of sense, because if you are able to do that, you can get a new set of images, as many images as you had at the beginning, but now all the conformations of those images are more consistent. They are kind of in the same conformation. So if you do a reconstruction, you will get a map that has better resolution and has improved density in those areas that are kind of blurry due to these motion blur artifacts. And this is what we have done with a new reconstruction method we have developed, which we call SART, which is an ART-based method that is able to use the information of the deformation field to correct the heterogeneity of each single particle during the reconstruction process. And this improves the resolution of the map. So I'm going to show you again the three examples I showed you before, but now using the SART. So in the first case is this CCT transition. We know it's phantom data. And the idea of this phantom data is just to test this idea of undeforming the conformations works. So if we want to undeform the conformations, for example, of the blue particles, purple, the yellow, red, and purple particles, or pink particles, to get the reference map, the idea is to take only those, trying to undeform them, and reconstruct the reference. If the process works, we should get something similar. Here in this video, you can see the comparison. You can see the blue map, which is the SART reconstruction, and the green map, which is the actual reference map. And as you can see, we are able to get pretty well the same conformation in this comparison. So this process of undeforming works fine. What happens if we apply this to real data? So for example, in this Empire 10,028, here you have the reconstruction done with CryoSpark. And here you have the reconstruction we obtained with the SART after undeforming all these conformational changes. And just by looking at the maps, we can already see a very nice improvement in areas that are moving, like for example, the small subunit. But if we do kind of a quantitative analysis with a local resolution, and we have a look at the local resolution slices, we really see that we are getting an improvement in the resolution of the maps. So actually, we are able to undeform the conformation and we are able to push the resolution. And something similar happens with the spike of this Oneup confirmation that I showed you before. So this is the map that we obtained with CryoSpark, and this is the map obtained with SART. And as expected, we see improvement in resolution mostly in the entities and the RBD, which are the regions that are moving more in the spike. And if we do a comparison of the local resolution slices, again, we see an improvement and mostly in the entities and in the RBD region. So really, we are able to correct the conformational changes to get a better reconstruction from the maps. And just to do a sum up of the presentation, so we have been talking about this new Zernikes3D approach. We think it's a very versatile method, not only because it allows you to estimate per particle conformations, but also because it allows you to do combined analysis. So now you can take volumes, in the future subtomos, atomic structures or particles, and put all of them in the same space. So now you can compare all those different conformations and see how they relate to each other, if they are represented or not. Also, it's very useful to estimate continuum heterogeneity to actually see the transitions and the motions of the molecule from the conformations of your particles. But also, as we can say, we have seen we can undo the conformations in order to recover a map that is reconstructed with a set of particles that is more consistent. So we are able to improve the resolution of our maps. And I would like to finish this presentation thanking the biocomputing unit for giving me the chance to do this PhD with them in this very interesting topic of continuum heterogeneity, and also all the economical support that is making this project possible. Thank you so much for your attention, and if you have any question, I will be very happy to answer.